Welcome back. Today we're going to talk a little bit more about functions. Going to redefine functions. We'll do a little bit more mapping with functions. We'll talk about domain and range and determining whether an equation or an inequality or a fraction is a function, and we will also determine the domain and the range of that. And then we'll also talk about function notation. Which can be a little fun and interesting as well. And it's just another way of exploring mathematics and knowing more of the vocabulary of math. So let's talk about functions. Our definition of functions. Here are really three different definitions of functions, or three different ways to say the same thing. A function is a relation that for each value of the first component of the ordered pair, so each value of the first component, so the x, there is exactly one value of the second component, or y. So these first two ordered pairs demonstrate a function. My first component is 3, and it leads to 4. And negative 4 leads to 7. So these two make up a function. Whereas in this pair of ordered pairs, 1, negative 2, and 1, negative 7, well, we have the first component leads to negative 2, and then the first component, the same one, 1, leads to negative 7. Okay, so we're not leading to exactly one value of the second component. 1 leads to negative 2, and 1 leads to negative 7. So that's a relation. That's not a function. Second way to look at a function, a set of distinct ordered pairs in which no first component is repeated. So here in this pair of ordered pairs, 6, negative 14, and 12, negative 14, the second component is repeated, but the first component isn't. So as long as the x doesn't repeat and lead to different y's, well, this is still a function. Whereas once again, just like we had in the previous problem, 1 leads to both negative 2 and to negative 7. No good, not a function. Whereas even though our outputs are the same, our inputs are different. So the first pair of ordered pairs is a function. And then the third definition, a correspondence that assigns one range value, one y value, to each domain value, or x value. So if we have our mapping diagram here, the domain and the range, where negative 12 leads to 4, pi leads to 26, 17 leads to negative 5, that is an example of a function. Okay, and as we showed in the previous example, if let's say 12 leads to negative 4, and even if pi leads to negative 4, okay, that would still be a function. Even though they have the same output, we have different inputs leading to the same output, so that would still be a function. Let's move down and let's talk about whether each of these is a function, and then let's explore the domain, the valid inputs. So we want to know what our valid x's are when we talk about domain. So when you see domain, think valid x's. So our first function, y equals negative 2x plus 7, well, that's simply an equation of a line in y equals mx plus b format. We know that's a linear equation, negative slope. Okay, sketch that graph real quick. That's a graph that might look something like that. We know that graph passes the vertical line test, so yes, this is a function. What are my valid inputs? Well, it's a line. What can I input for x, my valid inputs? Well, a line, I can put in any x value that I want. So my domain is all real numbers, or I think as the book will say, all the x's from negative infinity to infinity. Sample number 2, a little different. Y equals the square root of 5x minus 6. Well, is this a function? Yes, this is a function. We're only going to have, for each x value, we're going to only get one y value, one output. However, what about the domain? What are my valid inputs for this thing? What can I input for x? Well, this is a square root, and don't I know I can't take the square root of a negative number? So that means that 5x minus 6 has to be greater than or equal to 0. So if I add 6 to both sides and solve for x, I get 5x is greater than or equal to 6, and divide by 5, x is greater than or equal to 6/5. So my valid x's here, my domain, is any x. I can use any x that's greater than 6/5. Okay, so my domain 6/5, and I can include 6/5 all the way to infinity, or all real numbers greater than or equal to 6/5. So just for kicks, if I tried to take the square root of, and I put 1 in, 5 times 1 minus 6, y equals the square root of negative 1, well, I can't do that. So 1 is an invalid input. So only my valid inputs are 6/5 or greater. Sample number 3, y is greater than or equal to 4x plus 2. You may have seen this, but this is the equation of an inequality. This is that shading on a half plane. Okay, this graph looks, we've got a positive slope of 4, a y-intercept of 2, so our graph looks something like that, and we would shade like this. So is this a function? For every x, am I going to get one y? Well, no. As it turns out, in this particular graph, if I choose x equal to 1, I could get an output here, I could get an output here, I could get an output here. Those are all valid solutions. So this is not a function. So, not a function. But my domain, this is a linear equation, or linear inequality. And can I put any number in I want for x? I sure can. I can put 0 in, I can put negative numbers in, I can put positive numbers in. So my domain here is all real numbers. So, or we could say from negative infinity to positive infinity. Our fourth sample problem, we've got a fraction, y equals 6 over 5 plus 3x. Now this is also a function. Okay, I'm only going to get one output for y. For any individual x, I'm not going to get multiple outputs for y. So let's take a look at this. We've got x in the denominator. And so what's my domain? What are my valid inputs? Okay, determine that this is a function. But our valid inputs, well, denominator better not equal 0. So 5 plus 3x, okay, can't equal 0. So if I subtract 5 from both sides, I get 3x can't equal negative 5. I divide by 3, I get x can't equal negative 5/3. This is a single value that I cannot input for x, because if I do, the denominator will collapse and become 0. Okay, so that would make that function undefined. We don't want that. So all real numbers except negative 5/3, or from negative infinity to negative 5/3, non-inclusive, in union with negative 5/3 all the way to positive infinity. So there's our interval notation kind of squeezed into the bottom of the page there. Let's take a look at function notation. I think function notation is kind of cool. It's really, function notation is just a fancy way of saying y. So function notation, in function notation, y is f of x. And we call this f of x, not f times x. Okay, so if we go back and we look at our ordered pairs are x's and y's. They're inputs and outputs. They're independent and dependent variables. They're even domain and range, but now they're also x and f of x, because y is f of x. So we can rewrite our ordered pair as x and f of x. So if we have something where x is 2 and y is 13, that would be the ordered pair 2, 13. That means if we input 2 for x into a function, our output, y, will be 13, or f of x will be 13. And we'll do some samples of this in a minute. So slope-intercept form, near and dear to our heart, we know that's y equals mx plus b. Well, we can also write that as f of x equals mx plus b, where x, whatever we choose for x, is the input, and this whole right-hand side becomes our output. And we actually had a problem like this on the most recent test. I'll talk about that in just a second. Now, not every function is f of x. Really, the f is the most common that we use. But don't be thrown if you see like g of x equals, or t of x equals. That's just the name of our function. Our function is named g. Our function is named t. And then x is the variable that's in that function. We could even have like z of p. So our function is z, and then p must be our inputs. So we could have p squared minus 2p plus 1. Okay, so that would be the function z of p. We input p. Okay, here our input is x. So we had a question on the most recent test where cost was equal to like 700x plus, I don't know, 30,000. Where our output was our cost based on the number of items. And it said, oh, if we had 900 items, what would our cost be? So our function f of x would be 700x plus 30,000. And then we said, oh, input 900 wherever there's an x. 700 times 900 plus 30,000. And we found our answer. So that's how you'd get that started, and you'd finish that off. And if my memory serves me correctly, f of 900, this was 63. We got a final answer of 660,000. So let's take a look at some functions. If we're given the function f of x equals 5x minus 1, and the instructions are to find f of 2. That means put 2 into everywhere there's an x in that particular function. So put 2 into the function for every x. So f of 2 would equal 5 times 2 minus 1, because our function is the 5x minus 1 function. And 5 times 2 is 10, minus 1 is 9, so f of 2 is 9. So when we input 2 into this function, we output 9. You could also find like f of m plus 2. So we have our same function. Our f function is the 5x minus 1 function. The 5x minus 1 function is a function where we take our input, we multiply it times 5, and we subtract 1. That's what that function does. So now we're going to find f of m plus 2. So we want to replace every x in the function with m plus 2. So f of m plus 2 equals 5x, which is now m plus 2, minus 1. As we continue to solve, that's 5m plus 10 minus 1, and that's 5m plus 9. So f of m plus 2 equals 5m plus 9. That's our answer. Let's continue on with a new function, a new sample problem. If g of x equals negative 3x plus 5 divided by 2, our function now is g. The g function is we take our input, we multiply it by negative 3, add 5, and divide it by 2. That's what this function does to our input x. So we want to find f of negative 3. Oops, I have a mistake. We don't want to find f of negative 3. We want to find g of negative 3. So let me correct that. So g of negative 3 and g of t, because our function's name is g. So now we're in good shape. So g of negative 3 equals negative 3 times, well, negative 3 plus 5 all over 2. G of negative 3 equals 9 plus 5 is 14 over 2 equals 7. So that means I have the ordered pair, negative 3, 7. When I input negative 3, I output 7. And then also asked me to find g of t. Well, that says just put t into everywhere there's an x. So g of t equals negative 3 times x. So I put my t in there, plus 5 all over 2. So g of t equals negative 3t plus 5 over 2. And you might get a question like this. We want to rewrite an equation using function notation. Okay, so our equation is x squared minus 4y equals 3. So the first thing we want to do is we want to solve for y equals, because we really know function notation, f of x, or in this case, yeah, f of x is going to be is equal to y. So we want to solve the equation for y equals. So I'm going to subtract x squared from both sides. And I'm going to try and isolate y. Negative 4y equals negative x squared plus 3. I'm going to divide both sides by negative 4. And I get y equals negative x squared plus 3 all over negative 4. Or we could look at that as y equals, I have negative x squared over negative 4. That's the same as positive x squared minus 3 all over positive 4. That's a little bit cleaner. So our new function actually is f of x equals x squared minus 3 over 4. So I've done question 1. I've rewritten that using function notation. Part 2 says find f of 1. Well, that means we have to put 1 into the equation everywhere there's an x. So f of 1 equals 1 squared minus 3. And notice I'm showing my work all over 4. So f of 1 equals 1 minus 3 over 4 equals negative 2 over 4 equals negative 1 half. So f of 1 equals negative 1 half. That is the ordered pair, 1, negative 1 half. And they also asked me to find f of a. So f of a, we substitute a into our function. Our function was x squared minus 3 over 4. F of a equals a squared minus 3 over 4. So a little bit of experience with function notation. I'll probably cover some more samples in class. but this is a really good start. So we will see you in class.